Topic 3.1, Simple Harmonic Motion. Under this topic, what we are going to learn about is a specific type of motion. For example, the best example for simple harmonic motion, where we can see our day-to-day activities, is the pendulum of a clock. If we think of the motion of a clock, there are several features we can understand. The simple pendulum, the simple pendulum motion, the pendulum of a clock is called a simple pendulum. Simple pendulum motion is around towards both sides of some central equilibrium position. That is a characteristic of simple harmonic motion. A simple harmonic motion is always towards back and forth of a equilibrium position. And also, there are two extreme ends. The maximum displacement towards any direction is called the amplitude of simple harmonic motion. Amplitude. Here, in case of a simple harmonic motion, it is an angular displacement. So this is the displacement, the maximum displacement towards any direction, and there is a frequency. There is a frequency because this is a back and forth motion. It is a cyclic motion. So how many complete cycles per second? And that is the frequency. Therefore, always there's a frequency with respect to a simple harmonic motion. And also there's a period of time, that is the time taken for completion of one cycle. As usual, the relationship between frequency and time, we know F will be equal to 1 by T. F is measured in hertz, time is the T period is measured in seconds. So, and also another example for simple harmonic motion is if we think of a mass hung by a helical string. If we displace it slightly from the equilibrium position, displace slightly from the equilibrium position and then release, then it will undergo a simple harmonic motion. Same thing happen for a mass mounted on a helical string also. If we displace this from the equilibrium position, if we displace slightly from the equilibrium position and then release, we'll undergo a simple harmonic motion. So these are also examples of simple harmonic motion. If we look at the displacement time variation of this any type of a simple harmonic motion, we can see a similar pattern of displacement time graph. the displacement time graph of a simple happening motion is always have a, a, a variation like this. Which is a sinusoidal form. This is called a sinusoidal form equal to the variation of sine theta. The displacement may be either linear displacement or angular displacement. So displacement time graph is a sinusoidal curve. The equation of this type of a curve can be expressed as S equals A sine omega t, where S is the displacement, S or theta, as the case may be. A is the amplitude, that is the maximum displacement towards any direction. Omega is a constant for the omega is the constant. Omega is a constant for a sinusoidal. The omega is a constant for the simple harmonic motion. Yeah, omega is given by 2 phi f. Omega is given by 2 phi f. It is a constant dependent on frequency of the simple harmonic motion. T is time. This is usually expressed as x equals a sine omega t. Displacement is denoted by x. That is the usual practice. By using this relationship, we can derive expression for velocity, because velocity is, we know, the rate of change of displacement, that is dx by dt. Dx by dt. That is the rate of change of displacement. Therefore, we can write velocity equals, mathematically we can derive this. You need not know the derivation method at A level course. We can directly use this expression as minus A omega cos omega t. And the acceleration is dv by dt, that is the rate of change of velocity, is given by A equals A squared A omega squared sine omega t. A omega squared sine omega t. So x displacement is A sine omega t. The acceleration is A omega squared sine omega t. Therefore, we can see that combining these two relationships, we can write that x equals A omega squared. So A equals, that is acceleration equals omega squared x. Omega squared x. Omega squared x. Really, here I made a mistake. This is velocity is a omega cos omega t. Acceleration is minus a omega squared sine omega t. Therefore, this is acceleration is minus omega squared x. Acceleration is minus omega squared x. Therefore, usually this is taken as the governing equation of simple harmonic motion, which relates acceleration and displacement in terms of the constant omega.